Welcome to Study Loop.
All right. So for this problem, so we have this hydrogen gas, and remember that hydrogen is a bioatomic gas. Let me see else. So we have three processes: A, B, B, C, and CA. In process A, B, the volume is constant. In process B, C, the temperature is constant, and the CA, the P is constant. So part A is asking that what is the volume at point C? Okay, so to find out this volume, we need to start from the state A. Sorry, state B. Yeah, we need to use the state equation P V equal to nRT. So we will have PB VB equal to nRTB. Sorry, this is a small b. That's not that big. And also we have PC VC equal to nRTC. All right. So you just use uh, this equation divided by this equation, and you will obtain the equation VB over VC equal to TB. Uh, no, not TB. So what I want to say here is PB times VB divided by PC times VC equal to 1. That's because TB equal to TC, because this is in the process BC, the temperature is constant. So temperature at state B is equal to the temperature at state C. So this is equal to 1. In that case, we can solve for VC. So VC equal to PB VB over PC. All right. We can read the pressure and the volume at state B, and also we have the pressure at the state C. So just plug in the numbers, and also remember that you need to transfer the unit into the standard unit. So finally, I found that VC equal to 0.8 liters. So this is VC. Part B, we need to find out the temperature at the three states. At state B, again we have this state equation, right? And also we can read the VB from the diagram, and also we know the amount of gas, and R is a constant, so we can just calculate TB directly. But also remember to transfer the unit into the standard unit. So the standard unit is 1 atm, 1 atmosphere equal to 1.01 times 10 to the 5th Pascal. And 1 liter is 10 to the negative 3 meters cubed. All right. So you just need to plug in the numbers into the state equation, and you can solve for TB equal to TC because these two temperatures are the same. So temperatures are 1214.8 Kelvin. And TA, so to find out TA, you need to utilize the state equation at point A, just PA times VA equal to nRTA. And also you can read the volume and the pressure at state A. So it is straightforward. The calculation is very straightforward. So TA is 303.7 Kelvin. So that's the temperatures at the three states. And part C, we would need to find out the heat flowing into or out of the gas in the three processes. And also in part D, we need to find out the change of internal energy in the three processes. So we will combine the part C and part D together. Okay. So this is also for part D. To figure out the change in internal energy and also the heat into or out of the system, uh, I find it's more convenient to do the calculation of the change in internal energy. Firstly, that's more convenient. So, for example, in process AB, the change in internal energy delta U, the change in internal energy in delta A, in process AB is we just utilize N times CV times delta T. Okay, so N is the amount of gas, which is 0.004 moles. CV is the specific heat capacity of the hydrogen. You can look up this number in your textbook. The number I found is CV equal to 20.42. The unit is, let me see, joules per mole times Kelvin. So that's the number I found in your textbook. And delta T, because we're looking at the process AB, so delta T is TB minus TA. So we have this TA, we have this TB, so just plug in the numbers, and we can see the final result for delta AB, delta UAB, which I found is 74.42 joules. All right. And in the process AB, as you can see that the volume does not change, which means the work is 0. And you'll see that in that case, the Q, the heat flowing into the system equal to delta UAB, which equal to 74.42 joules. Okay, so this result tell us that in process AB, the heat flowing into the system is 74.42 joules, and the change in internal energy is also 74.42 joules. In process BC, because the temperature does not change, so delta U is 0. So the internal energy does not change. And the work, there's a formula in your textbook which is related with the work for a constant temperature. The relation is the formula is nRT times log. This is natural log. The V final in the process BC will be VC divided by VB. Okay. So the temperature is constant, so we can just label by PB in this case. So N is 0.04 moles, R is the constant, TB is calculated as this one. This is TB, and VC is 0.8 liters. The VB is 0.2 liters. So we can calculate this work directly. The work is 56.00 joules. In this case, this also equal to the heat flowing into the system because WEC is 0. Okay, this is for BC. And for the process CA, there is not much space for me. I'll try to make some space. I write it here. So for process CA, firstly we can see the delta U CA. because the internal energy only depends on the temperature, and we already know the temperature at the state C and the state A, that is Tc and Ta. So we can figure out the delta U Ca directly, which equal to N times Cv times delta T. And delta T in this case will be the Ta minus Tc, because A is the final state, C is the initial state. So the value is negative 74.42 joules, so which is just opposite to this one. Okay. And the work done in this process, as you can see, that in this process, the so this is AC. The pressure is a constant, so the work formula is easy. So it's simply P times delta V, and delta V equal to VA minus VC. So the work is negative 30.30 joules. So the first thermal law tells us that QCA equal to delta UCA plus work CA, this one. So you just need to add these two numbers together. So which gives you 104, sorry, negative 104.72 joules. So this number is a negative value. It means that the heat is flowing out of the system, and the amount of heat is 104.72 joules. So that's it.